Assalamualaikum and hi everyone, my name is Akmal Zahira binti Zwasni, and today we are going to present a metallurgy case study for EMT2083 where we are looking at 4 different metals used in manufacturing, which is mild steel, aluminium, stainless steel and copper. So each of these metals behaves very differently, which is why engineers choose them for different types of jobs. In order to choose the right metal safely, we need to understand 3 main things. So the first one is tensile properties, which basically means how strong the metal is when you pull it until it stretches or breaks. The second one is toughness, which is how much energy the metal can absorb before it snaps. And the third one is turbidity, which tells us if a metal will suddenly become brittle and shatter when it gets to freezing cold. If we ignore these facts, structures can fail without warning, just like what happened to the famous Liberty ships that cracked in cold waters during the World War II. So now, let's see how these metals stretch, and I will pass this to Sophia.
Hi, Assalamualaikum. My name is Nur Sofia binti Azli. My metric number is J24A1015. Today, I will present about tensile behavior comparison, tensile properties of metallic materials. Material that we study is mild steel, aluminium, austenitic stainless steel, and copper. There are 4 properties that we compare between yield strength, ultimate tensile strength, UTS, ductility, and strain hardening. Now I will explain about stress strain curve characteristic. The figure 2.1 is typical stress strain curve of mild steel, aluminium, austenitic stainless steel, and copper. The key observation of this figure is mild steel show a distinct yield point, aluminium shows smooth yielding behavior, stainless steel has a higher strain hardening, copper show excellent ductility. Different curve indicate different mechanical properties. As we can see in the figure, austenitic stainless steel has no distinct yield point, very high wood hardening rate and higher strength. And then we can see the second one in the blue color is mild steel. Distinct yield point phenomenon, upper and lower yield point, followed by strain hardening. And then for copper, no distinct yield point, but excellent ductility. And then the most lowest is aluminium, no distinct yield point, but smooth yielding and moderate strain hardening. The first properties that we compare is yield strength comparison. Yield strength is stress at which permanent deformation begins when we do the tensile testing. As we can see in the table, stainless steel show a highest yield strength, meanwhile mild steel show a moderate yield strength. And aluminium and copper show low yield strength. Stainless steel and mild steel can withstand higher loads before permanent deformation, meanwhile aluminium and copper can withstand low loads before permanent deformation. The second comparison that we're doing is ultimate tensile strength comparison. UTS is maximum stress before necking and fracture that happen during tensile tests. As we can see in the table, stainless steel show a very high ultimate tensile strength. Mild steel show a high ultimate tensile strength. Meanwhile, aluminium and copper show moderate ultimate tensile strength. Stainless steel has the highest UTS due to strong strain hardening. The third one is ductility comparison. Ductility is the ability of one material to deform before fracture. As we can see in the table, stainless steel and copper show an excellent ductility, meanwhile mild steel and aluminium show a good ductility. Copper and stainless steel can undergo large plastic deformation before breaking. Okay, so the last one is comparison of tensile properties. As we can see in the table, stainless steel show the best overall tensile performance. As we can see, stainless steel show a very high yield strength, very high UTS, excellent ductility, and very high strain hardening. Meanwhile, might still provide a balance between strength and cost. As we can see in the table, might still show a moderate yield strength, high UTS, good ductility, and moderate strain hardening. Meanwhile, aluminium is suitable for lightweight application. Aluminium show low yield strength but moderate UTS, good ductility, and moderate strain hardening. Copper is highly ductile and easy to form. As we can see in the table, copper has low yield strength, moderate UTS, excellent ductility, and high strain hardening. That's all for me. Thank you.
Now, if we look at the stretching curves that we just showed you and discussed earlier, you will notice something strange. While aluminum, copper, and stainless steel stretch smoothly, mild steel does something that is completely different. It shows a unique behavior called the yield point phenomenon. So as you can see on the graph here, when you pull mild steel, the stress goes up to a peak called the upper yield point, then it suddenly drops to a lower yield point. After that, it bounces along a flat line, forming that what we call Zuder bands, before it finally gets stronger again. So in manufacturing, knowing this exact drop is super important because it shows the exact moment where the metal actually permanently changes its shapes. So the question is, why does this only happen in mild steel? It's because due to its BCC crystal structure and a tiny atomic trap called a Cortwell atmosphere. So inside the mild steel, the spaces between the iron atoms are very small and cramped. And because of this, tiny carbon and nitrogen atoms like to crawl and hide right underneath the dislocations, which are the internal lines where metal slips. So these carbon atoms form a little cloud that locks the dislocations in place. So in order to make the metal stretch, you have to pull extra hard at first, which gives us the upper yield point just to rip those lines away from the carbon clouds. And once they are break free, it becomes much easier to pull, which causes the sudden drop to the lower yield point. Other metals like aluminum, copper, and stainless steel don't do this because their internal spaces are larger and more open, so carbon atoms cannot lock them in place.
Assalamualaikum. My name is Zikri Nur Fahmi bin Muhammad Nasri and my metric number is J23A0517. And now I will explain the toughness analysis. Toughness is the ability of a material to absorb energy before it fractures. It is represented by the total area under the stress-strain curve. A large area under the curve means the material has higher toughness because it can absorb more energy before breaking. In general, ductile materials have higher toughness than brittle materials because they can undergo more plastic deformation before fracture.
So next, in this slide, I will explain about the brittle to ductile transition, temperature or DBTT. So DBTT is the temperature at which a material changes from ductile behavior, where it can deform before breaking, to brittle behavior, where it fractures suddenly with little or no deformation. So as shown in the graph, this phenomenon mainly occurs in basic metals such as mild steel. So when the temperature decreases, the impact energy also decreases. So meaning that the material become less tough and more likely to fail by brittle fracture. So on the other hand, FCC metals including aluminium, copper, and austenitic stainless steel remain ductile over a wide range of temperatures and do not show a significant DBTT. So while we're looking at the graph, the left side represents the brittle region with low impact energy, while the right side represents the ductile region with high impact energy. So the middle section is the transition region where the material changes from brittle to ductile behavior. So understanding DBTT is important because it helps engineers select suitable materials for low temperature applications and reduce the risk of unexpected brittle failure in engineering structures. Now that we understand what DBTT is, so now let's look at the crystal structures that determine whether a material experiences this transition. So a crystal structure refers to the arrangement of atoms within a metal. So this atomic arrangement influences the material's mechanical properties and how it behaves at different temperature. So the first structure is the body-centered cubic or BCC as shown in the figure. So atoms are located at the 8 corners of the cube with one atom at the center. Must has a basic crystal structure. So because of this arrangement, it is more sensitive to low temperature and can undergo a ductile to brittle transition, which we discussed in the previous slide. Okay, next for the second structure is the face-centered cubic, or we call it as FCC. In this structure, atoms are located at the 8 corners and the center of each face of the cube. So aluminium, copper, and austenitic stainless steel are example of FCC material. So unlike BCC metals, FCC metals remain ductile even at low temperature and therefore do not exhibit a significant ductility. So after understanding the two crystal structure, let's compare their characteristic and show in the table. So the main difference between BCC and FCC is the number of the active slip system. So BCC metals have fewer active state system, which make dislocation movement more difficult, especially at low temperature. So as a result, BCC materials such as mild steel become brittle and exhibit a ductile to brittle transition temperature. So in contrast, FCC metals have many active system, allowing dislocation to move more easily. So therefore, aluminium, copper, and austenitic stainless steel remain ductile and maintain high toughness even at low temperature. So this is why FCC materials do not exhibit a significant ductility. So based on the mechanical properties and low temperature behavior discussed earlier, the different materials are recommended for different engineering applications. So first is mild steel is the best choice for structural application because it has high strength, good toughness, and is cost effective. So these properties make it suitable for buildings, bridge, and other load-bearing structures. So second is aluminium. It is recommended because of for their lightweight applications due to its low density and high strength to weight ratio. So this helps reduce the overall weight of product while maintaining adequate strength, making it widely used in the aerospace and automotive industries. So for cryogenic applications, the most suitable material is austenitic stainless steel. Since it has an FCC crystal structure, it does not exhibit a significant ductility, and as a result, it remains tough and ductile even at extremely low temperature, so making it ideal for LNG storage tanks and cryogenic equipment. So finally, copper is preferred material for electrical application because it has excellent electrical conductivity and good ductility. So these properties make it standard material for electric wiring, power transmission, and electronic components. Thus, selecting the appropriate material depends on the required mechanical and physical properties by the application. So by understanding the difference in tensile behavior, toughness, and crystal structure, engineers can choose the most suitable material to ensure both safety and performance.
In conclusion, tensile properties, toughness, and the ductile to brittle transition temperature are important in evaluating metallic materials. Understanding these properties helps engineers select the most suitable material for different engineering applications, ensuring better strength, safety, and reliability. That's all from me. Thank you.